Hello everyone. This fluid machinery lecture is about water hammer. Sounds interesting, doesn't it? So as an introduction, so far we dealt with steady state operation of pumps. Okay, so whenever we computed the pressure drop or the velocity triangles, etc., we always assumed that the flow is established, okay, and it's constant. It's time to deal with unsteady or transient phenomena. When can this happen? For example, when you start a pump. Okay, so either directly, so just switching a button and then the electric motor is up and running and it's driving your pump, or by a frequency converter, which you can program, for example, to start the pump within whatever, 20 seconds, 30 seconds, 7 seconds. That's a startup process, meaning that the flow rate is not constant, but the flow rate and hence the velocity, the flow velocity in the pipe is changing. Another example would be the pump shutdown. So when you switch off your pump, either directly, so just hitting a button and then letting it run out, or with a frequency converter again, or more importantly, due to an electric failure. So imagine that you have a couple of pumps running, and then you have an electric failure. Electricity is gone suddenly, and then they will stop and run out. And the change in the velocity will result in a change in the pressure, in other words, pressure waves, shock waves running through your system, and this can have very serious consequences. On the left-hand side, you have a pipe which is burst by a high pressure peak, whereas on the right-hand side, you have compensators that are damaged or they collapsed due to vacuum. So this is overpressure, this is vacuum, both of them caused by hydraulic transients. Okay, so let's have a look at this figure, left-hand side. I have a reservoir, I have a tank, and I have a valve at the end of the pipe. On the right-hand side you see the same, but here you have the valve is located at the beginning of the pipe. In both cases, the flow velocity is v and it's steady. So for example, at t equals 0, the velocity is this value, the pressure is this value, and then I suddenly close this valve, okay? So suddenly I close it. That will result in a velocity change. So if I do not close it entirely, then the velocity will drop, okay? And there will be a shock wave running through the pipe backwards. Probably the easiest bit is to imagine the water as a series of masses connected by springs. Or you can also think of it as cars in a traffic. And then what you do is you suddenly stop the first car. So the first car is stopped, the rest one is coming with a velocity v, and then after some time the second realizes that the first stopped, so it will also stop, but still it needs some time for the third one to realize that we need to stop. So there will be a wave running backwards with sonic velocity a. To the left of the wave, everything is unchanged. These cars don't know yet that the traffic light is red here, whereas these cars already stopped because they see that the traffic light is red. Now this was velocity. In terms of pressure, there will be a pressure rise here. I think you can easily imagine it again, that all these masses, all these cars are running from the left to the right, and then you suddenly stop it with your hand here. So then you will experience a pressure rise, an extra force that you need there to keep these cars or their masses at rest. Okay, so sudden valve closure at the end of the pipe, velocity drops, pressure rises. This is important. Now, if you do the same here, and you have again all your small masses here that are happily traveling to the right, and then out of the blue, suddenly you stop the first one. So now this one, you stop. Then the same happens, that this stops and after sometimes the next will stop and the next will stop. So now you will have a depression, a shock wave running from the left to the right. To the left of the shock wave, everyone is standing or the velocity is lower. To the right, nothing happened yet. But now, instead of a pressure rise, you will have a pressure drop. Okay, because your springs are elongated. Here they were compressed, here they are elongated. So here you have a pressure drop. And now what we want to do, we want to relate the velocity change and the pressure change. Okay, because usually I know the flow rate in my pipe. If I close the valve, I know what delta V is, and I want to work out what will be the pressure difference due to this velocity change. And again, don't forget, if you have valve closure at the end of the pipe, then you have a pressure amplitude added to the basic pressure. If you have a sudden valve closure at the beginning of the pipe, then you have a pressure drop. Okay. So now we open the fluid mechanics textbooks and use the control volume concept. So along the shock wave, you get a control volume. This is the pipe. So to the left, this is the shock wave here. To the left of the shock wave, nothing happened yet. So you have the usual diameter, and velocity and pressure is the undisturbed value. Whereas to the right of the shock wave, you have an expansion of the pipe because of the larger pressure. So the pipe diameter is larger and the velocity is smaller. But our problem is that this shock wave is moving to the left. So this is in the standing frame of reference. We cannot apply the control volume concept because the shock wave is moving, but it's relatively easy to get over it. Oh yes, but before we do that, for the ease of computation, we will assume that the velocity change is such that here the velocity is 0. So actually it will look like this. Okay, so in other words, I will fully close the valve here. Okay, so now I will, instead of this control volume, I will move my control volume to the left with the sonic velocity A. And now I can compute, I can apply the momentum theory. So guys, this is standard fluid mechanics. Please have a look in your lecture notes, what you learned from Mr. Professor János Vad in fluid mechanics, or if you did fluid mechanics in your home university, then open your textbook, you will find this in momentum theory and control volume concept. What we need is pressure and impulse forces. The pressure forces are always pointing into the volume. The impulse forces are pointing out. This will be cross-section 2. This here will be cross-section 1. So for example, this is P1 pointing into the control volume, and this is I2 pointing outward. Now the pressure forces is A times P, which is the pressure force on this surface, and delta Ames times P times delta P, which is the pressure force on this surface. So the surface is delta A and the pressure is larger because that extra pressure makes the diameter to extend. Impulse force is always mass flow rate times velocity. So velocity is V plus A at location 1. Okay, and mass flow rate is rho AV plus A. So this is the impulse force here. The impulse force on the other side is A squared times the density increased, and the area is also larger here. And the pressure force finally at point 2, location 2, is simply pressure times area. We have one more equation, which is the continuity equation, which should be true. So the amount of mass flow rate entering here, rho A plus V, is the same as the amount of mass flow rate leaving here, which is A times rho plus delta rho A times delta A. This is all we need. We put all these equations together, as you can see here. So here I did nothing, just apply the momentum theory, and I wrote out all the terms. Now it's nice that the momentum equation appears. So the red terms cancel each other because of the momentum equation. And the blue terms just simply appear on both sides. So they also cancel each other. And what you are left with is this remarkably simple equation. And now we think a bit about this term here. Sonic velocity in water is about 1000 meters per second. A typical flow velocity is around 1 or 2 meters per second. So you can happily neglect this V next to this A. So it doesn't matter if it's 1002 or 998. So at the end of the day, you are left with this very simple equation. Okay, and this is nice. But this equation holds only as long as the closure is fast enough. And by fast enough, we mean that the shock wave, which travels through the pipe with sonic velocity A, will need a time of 2L over A to run fully back and forth through the pipe of length L. Okay, and this will be called the characteristic time of the pipe. This is important. This is the characteristic time of the pipe because L is here. So if the closure is within this time, so if the closure time is smaller than the pipe's characteristic time, which is given by this equation, then you can use this formula to estimate the pressure difference due to velocity change delta V. If the closure time is much larger than the characteristic time, then you simply use Newton's second law of motion. So you simply need that I have this fluid column of length A, L, cross-section A, and density rho. So this is the mass of the fluid inside the pipe, and the acceleration or deceleration is approximately delta V over T close. And this results in a force delta P times A. So this is the second formula which you use for slow closing. Okay. Now let's speak a bit about sonic velocity. So sonic velocity is simply the response in pressure for a change in density. So you can also write this equation as delta rho times A squared equals delta P. So this simply tells you that if I change the density by delta rho, which is simply because I'm compressing the liquid, so this can be due to a volume change, the pressure difference, the pressure change will be A squared times this. So for ideal gases, the sonic velocity is kappa RT. For fluids, it's E over rho, just like for solids, where E is the elasticity modulus. For water, it happens to be 2.1 gigapascals. And thus, if you plug this number into this number and rho is 1000 for water, you will see that the sonic velocity in water is about 1400 meters per second. Now, in reality, when we are doing such measurements, then we always measure lower sonic velocities. Okay? So this is due to the elasticity of the pipe itself. Don't forget that the water is in a pipeline. So the pipe is also flexible, and thus you need to correct the elasticity modulus of the fluid with the elasticity modulus of the pipe. Delta is the valve thickness and D is the diameter. So, for example, if you have a polyethylene pipe whose elasticity modulus is around 600 to 900 megapascals, and the nominal pressure is 25 bars, diameter is 120 millimeters, and the pipe thickness, the valve thickness is 18 millimeters, then this will result in this reduced elasticity modulus, and this will be the sonic velocity of water in this pipe. Of course, if you put the same water into a steel pipe or a concrete pipe, a reinforced concrete pipe, then the sonic velocity will be much, much higher. Even more interestingly, if now you say that within this pipe I have a velocity change of 1 meter per second, this will result in 3.9 bars of pressure difference, extra pressure, okay? Don't forget, this extra pressure is superimposed to the system pressure, either in the positive or in the negative direction, depending on the location of your valve. Okay, so as a summary, we have learned that starting or shutting down pumps will result in pressure waves in the system, which are dangerous. And if the closure time is smaller than the characteristic time of the pipe, then you can use this very simple equation to estimate the pressure difference. And again, it's so important that I wrote it here again, that this is superimposed to the system pressure, okay? So let's say if the system pressure is 6 bars and this is 4 bars, then and if you're closing at the end of the pipe, then the overall pressure will be 6 plus 4, that is 10 bars. Whereas if you're closing at the beginning of the pipe, then the pressure will be 6 minus 4 bars, that is 2 bars. Now, it's very easy to get negative pressures. Negative pressure means vacuum. Okay, so this is the case when you're closing the valve at the beginning of the pipe. You can have vacuum, and vacuum is extremely dangerous. It's even more dangerous than the pressure peaks. Have a look at this tank, which was very easily damaged by vacuum. To put it another way, think about one of those plastic bottles you drink your favorite drink from, so Coca-Cola, Sprite, whatever, and you cannot blow it by yourself by blowing air into these bottles, okay? But you can very easily collapse it by sucking the air out of it, okay? So our pipes usually tolerate more or less extra pressure peaks, but our pipes are extremely sensitive to vacuum, and it's very important to avoid such situations. We have also learned that the pipe material and the valve thickness and diameter changes the sonic velocity significantly. It's very important what kind of pipe the fluid is in. And okay, what about protection? So what do we do? So first of all, you can use a damped check valve. So these are check valves which have some kind of damping mechanism, which, if the flow direction changes, doesn't allow the check valve to close immediately, but it will close regularly, and hence you won't get a sudden closure, but you'll have a slow closure. You can also use a surge tank or a standing pipe. So have a look at this figure. A surge tank is essentially a closed reservoir which is pressurized, and you have gas here above the water level. Now, if your pump runs out and it stops, then this pressurized gas will push the water out from the surge vessel, and it will replace the pump flow rate for some time, and hence the velocity change in the pipe will be lower. A standing pipe is something similar. So the standing pipe is the same as the surge vessel, it's just opened to the surroundings. If you have high pressures, then you will have inflow here, and it will dampen these high pressures. If you have vacuum or low pressure situation, then it will feed water back into the system to compensate for the pressure difference. Very often we use vacuum breakers. Okay, these are valves which open if there is vacuum in the pipe, okay, and by letting air into the pipeline system, it makes the whole system much softer and less prone to to pressure surges, and it can also release the air. So once the pressure is recovered and you have high pressure in the pipeline again, it can get rid of the extra air within the system. And finally, you can have artificially controlled valves for opening and closing. This is very important, okay? And again, sudden valve closure is very strongly related to the length of the pipe. Okay, so the same closure can be sudden closure for a very long pipe, and can be a slow closure for a short pipe. It all depends on the characteristic time of the pipe, which is 2L/A. Okay, so we have added some new material to the lecture notes. This is chapter 5.4. Please have a look at it, read it carefully. There are also problems added so that you can practice. And next week I will come again with a new video. Thank you for your kind attention. Have a nice week.